it makes an angle of 15. Makes an angle of 15 with the end direction. That's going to be in the positive end direction. So TAC times the cosine of 15 degrees, sum of forces has to equal 0. And now when you put in the numbers, TCD is still 294.30 newtons. Solve for a TAC, and we get the same 215 that we had before. Once you solve for the TAC, you can use sum of forces X, you can use sum of forces Y, you can use sum of forces in the T direction. Any of those would give TBC. Just because you use the normal for one direction doesn't mean that you have to use the perpendicular direction for the second equation. You can still go back and use either horizontal or vertical for the other equation if you want to. So the question is, did you really save anything by summing forces in the n direction rather than summing forces horizontally and vertically? Well, you avoided having to solve two equations and two unknowns, but the complication was you had to do a lot more geometry to find out what the angles were. Is it worth it or not? Up to you. Doesn't really make any difference. The author likes to say in various problems, reduce it to a single equation by summing forces in the proper direction, or reduce it to a single equation by summing moments about the right point. But if it takes you 2 weeks to figure out what point is the right point, you're better off just writing horizontal, vertical, and summing moments about any arbitrary point you want. It's always going to work. If you can't think of anything better, if you can't find any reason to do otherwise, summing forces horizontally, summing forces vertically, summing moments about any point will give you the answer that you're looking for. Another problem, we have this pole, has a mass of 150 kilograms. So if it has a mass of 150 kilograms, 150 times 9.81 is going to give us a weight of 1,471.5 newtons. It's 15 meters long, supported by a vertical wire attached at the 1/3 point, and I want to determine the reactions at A and B. It says smooth ends against vertical walls. So we're going to neglect any frictional forces at the vertical walls. I'm trying to relate the weight of that pole and the forces at the ends of the pole. So the free body diagram that naturally comes out is, let's draw the pole. I know what its weight is. I want to know what the forces at the end are. The weight acts at the midpoint. But we still have to talk about center of gravity, center of mass. We'll get to that a little bit later on. But for right now, we'll just say the center of gravity, the point where all the weight appears to be concentrated, is the midpoint for uniform objects. We have the tension, which is a vertical wire. Wires, ropes cannot resist motion perpendicular to the wire or rope. They can only exert a pulling force, stopping the rope or wire from extending. On the side walls, we're told that the ends are smooth, so there's no resistance to movement vertically. The only resistance is going to be horizontally, and the walls have to push on the object. The walls cannot pull. They're not glued. They're not attached. So I have normal forces, forces normal to the wall at each end. So this is my free body diagram. I'm going to have to use the angle that that pole makes with either horizontal or vertical. So let's go ahead and indicate that on there. I also have to know where some of these forces act. Now the tension is 5 meters from the left end, 10 meters from the right end. The center of gravity, the middle of the pole, is halfway over. So it's going to be 7.5 meters from either end, and therefore it's going to be 2.5 meters away from where that wire is attached. We have to do those calculations. Let's go ahead and put them on the free body diagram so we don't have to keep redoing them and sometimes getting them wrong. So I isolate the body. I make sure that wherever I've taken something away, I've included the effect of what I've taken away on what I've kept. That's the free body diagram. Show all forces acting by things that I took away. I had to cut the wire to isolate it from the ceiling. I had to separate it from the side walls, left and right. And I had to take the earth away, so I have to show the gravitational force acting on that pole. And now, for lack of anything better, I'll sum forces horizontally, vertically, and moments again. So that's what I'm going to do. And here's what it looks like for the particular problem. Summing forces horizontally. I've got NA minus NB equals 0. So that tells me immediately that NA and NB have to be the same. Doesn't tell me what either one is, but whatever they are, they have to be the same. Vertically, I've got T minus 1471.5 equals 0. So that tells me that T has to equal 1471.5 newtons. Sum of moments about any point have to be 0. I can sum moments about the left end. I can sum moments about the right end. I can sum moments about the mass center. I can sum moments about the point where the wire is attached. Doesn't make any difference. Except that to get something easy to solve, let's sum moments about a point through which pass at least one of the unknowns, as many unknowns as possible, get them out of the equation and allow me to solve for the rest of the unknowns. So in this case, I've got 3 unknowns, NA, T, and NB. Well, actually, I've been able to solve for T from that equation, so that kind of helps me out a little bit. Let me sum moments about, I guess what I chose to do was sum moments about the left end. That gets rid of NA. So if I sum moments about A and set that equal to 0, I'm going to have the force T times 5 cosine theta. Force times perpendicular distance between the line of action of the force and the point that I'm taking moments about. So 5 T times 5 cosine of theta. And that's going to give me a positive, a counterclockwise rotation around point A. This is the point that I assume is fixed. How do the other points move relative to it? The weight is going to give me a negative rotation, clockwise rotation around the same point. So that's going to be plus the weight, 1471.5, times 7.5 cosine of theta. And finally, the force NB passes above the point I'm taking moments about, so that's going to give, again, a counterclockwise rotation. I'm going to get plus NB times 15 sine of the angle theta equals 0. Well, I guess it's time to figure out what the angle theta is. Haven't gotten around to that yet. I know that the pole is 15 meters long. The distance between the two walls is 12 meters. and that's going to make this side be 9. It's a 3, 4, 5 right triangle. Theta is the angle whose cosine is 12 over 15. Theta is 36.870 degrees. So theta is 36.870 degrees. It's the angle whose cosine is 12 over 15. But again, it's basically a 3, 4, 5 right triangle. 3 times 3, 4 times 3, 5 times 3. So the sine of theta is going to be 3/5. Cosine of theta is going to be 4/5. And putting in cosine theta is 4/5, cosine theta is 4/5, sine theta is 3/5. Putting in that T is equal to the 1471.5 newtons. The only unknown left then is NB. I get NB is equal to 327.000 newtons. And NA is the same. So the final answer would be NA equals NB is equal to 327 newtons. The tension is equal to the weight is equal to 1471. Well, it depends on how you learn to round numbers off. If it's odd, when it's exactly half, if it's odd, we raise it to the next higher number. When it's even, we round it down when we're exactly a half. So 1472 newtons. Yeah. Enough on that one. Do your work neat. And then when you're reviewing it for a test, it'll make a lot more sense than just having a bunch of scribbles on a paper trying to get something that Wiley plus